Linear approximations. We are going to use a tangent line to approximate a function. So that's all we're really doing here. If you look at your handout, make sure your example 1 says what mine says. I did adjust it at some point. So what we're going to do is we're going to use the tangent line at x equals 4 to find an approximation for this function, the square root of x squared minus 3x, at x equals 5. So let's just remind ourselves, we want an equation of a line. So we're going to start with that, and the equation of a line that we want to use is the point slope. So y minus y1 is equal to m times x minus x1. So, okay, we've got this. What do we need? To write an equation of a line, we need 3 things. We need x, we need y, and we need slope, m. So let's go ahead and see what we can find. So it says use the tangent line at x equals 4. So that's the x value that I'm going to use as x is 4. Then I need to find what y is. Well, I know the function is this, so y is going to be the square root of 4 squared minus 3 times 4. And that works out to be the square root of 16 minus 12, which is the square root of 4, which is 2. So my y value is 2. The last thing I need is my slope of the line. Now this line is a tangent line to my function, so the slope of the tangent line is the same thing as the derivative. Okay, so all I really need is to find the derivative, and then I want the derivative at x is 4. So my derivative is going to be, oh wait, let me rewrite my function first. Let's rewrite my function in calculus-friendly terms first. X squared minus 3x is really raised to the 1/2. Now I can find my derivative using my power rule and my chain rule. So I bring the 1/2 down, x squared minus 3x is now raised to 1/2 minus 1, which is negative 1/2. I need to multiply by the derivative of the inside, which is 2x minus 3. So I'm going to rewrite that in not in calculus-friendly terms, but in arithmetic-friendly terms. So I really have a 2x minus 3 on the top. On the bottom, I have a 2, and I have a square root of x squared minus 3x. That is on the bottom because of the negative exponent that I have. So I don't want the actual derivative. I want the derivative at x is equal to 4. So now I need to find f prime at 4. And that is going to be 2 times 4 minus 3 over 2 times the square root of 4 squared minus 3 times 4. So that ends up with 8 minus 3 on the top and 2 times 2 on the bottom. I just evaluated the square root of 4 squared minus 3 times 4 when I found my y value. So that leaves me with 5 over 4. So my slope is 5 over 4. And I can now write that down as in what I need to know. At this point, I can write my equation. Y is going to stay y. I'm going to subtract my y1. M is going to be something. X minus my x1. And let's plug in what I have. My x value is 4. My y value is 2. And my slope is 5 over 4. Well, I don't know why I wrote 5 over 8. I apologize. This should be 5 over 4. Sorry about that. Great, so I've written my equation of my tangent line. I should be finished at this point. Well, not exactly. I need to actually use this equation to find my approximation. So at this point, I'm going to use this equation that I have here, to approximate my function value at x is equal to 5. So all I'm going to do is I'm going to say, okay, y minus 2 is equal to 5 over 4 times 5 minus 4. I'm plugging in x is 5. So where my x value was, I'm plugging in a 5. So I'm going to have 5 over 4 times 1 plus 2. All I did was add 2 to both sides, and then I also evaluated that 5 minus 4 is 1. And that leaves me with 5 over 4 plus 8 over 4, which gives me 13 over 4. So f of 5 is approximately 13 over 4. And there is my approximation. Moving on, we're now going to talk about antiderivatives. So what is an antiderivative? Well, it's actually exactly what it sounds like. We usually start with a function and then take the derivative of that function. And when we're doing that, we would use this kind of notation. Take d dx of y means take the derivative of y. When we're finding an antiderivative, however, we are starting with the derivative and trying to find the original function. We're going backwards. This is the notation, this little symbol means to find the antiderivative of y. So let's go ahead and let's do the first one. So we're going to evaluate the antiderivative of x squared minus 5x plus 3. So we're going to just do this one at a time. And if you wanted to, you could rewrite this as the antiderivative of x squared minus the antiderivative of 5x plus the antiderivative of 3. And if we wanted to simplify this a little more, we could also take our constants outside of the antiderivative symbol. If that is more confusing, then you don't need to do that. You don't even have to do the first step if you can see what it is we're doing and where we're going. Then you can just leave it alone. So the antiderivative of x squared. Well, if my derivative is an x squared, what did I have to start with? I had to start with an x cubed. However, when I take the derivative of x cubed, I get 3x squared. I don't have a 3 in my when I'm finding the antiderivative of. There's no 3, which means I want my 3 to really become a 1, so I need to multiply by a 1/3. So now, just doing a little note, I'm going to erase this. I just want to see what's the derivative of this one term. I would have 1/3 times 3x squared, and then my 1/3 times 3 is really just a 1, leaving me with just an x squared. So I'm confident in that first term that I have. Now I move on to the next one. My 5 is going to remain there, and now I need to figure out what I started with so that when I took the derivative I got x. Well, I had to start with an x squared. However, if I were to take the derivative of what I have right now, 5x squared, that would be 10x. But I don't have 10x, I only have 5x. That's exactly how much? Exactly half. So I need to multiply by a half. That right did not look good. So I'm going to multiply by a half. And the next one, I took the derivative and I got 3. So what do I have to start with? Well, I don't have any x's there, which means I had to have started with an x. And I take the derivative of 3x and I get 3. So I'm good. And then I have to add the c. So let's talk about what that means. In the next question it says, we need to take into account that there could be a constant you add to the antiderivative, and why is that? Well, when I'm taking the derivative of constant, it's 0. So the derivative of any constant is 0. Which means at any point I could have any number there, 5,000, negative 2.3, anything, but when I take the derivative of it, it doesn't appear anymore because the derivative is 0. So what that means is, all we're saying is that this plus c is just acknowledging that we know there could be something there. So we are acknowledging there could be some constant. And we're also acknowledging that we don't know what it is. And it being the constant. So let's go ahead and look at the next one. We've kind of jumped ahead pretty quickly. The first example was polynomials, and now this example is trig. So I need to figure out this little puzzle. I took the derivative of something, and I got 6 sine of 2x. So immediately I need to know what I started with. And if I have a sine, then I know that when I started out, I had to have had some kind of cosine of the same thing. But let's think about this for a minute. When I take the derivative of cosine, I get negative sine. Well, there's no negative in my antiderivative up here, which means I really need a negative down here. So if I take negative 6 times the derivative of cosine of 2x, that's going to give me negative 6 times negative sine of 2x. But when I take the derivative of that thing, I still have to multiply by the derivative of the inside, and I would have me multiplying by 2. Well, I don't actually have that, which means in my antiderivative right now, I need to divide by 2. So I'm going to go ahead and put a divide by 2 in here. And then I need to acknowledge there could be any kind of constant there. So let's look at what we have. I have negative 3 cosine of 2x plus some constant. Let's check. So to check this, I'm going to say that y is negative 3 times the cosine of 2x plus some constant. Let's take the derivative now. So if I take this derivative, I should get what I started with. So when I take this derivative, I have negative 3. The derivative of cosine is negative sine of 2x times the derivative of the inside, which is 2, plus the derivative of a constant, which is 0. So let's regroup. I've got a negative 3 times a 2, times a negative. So I have a negative times a negative, which is a positive. I have a 3 times a 2, which is a 6. Then I have a sine of 2x. So is this what I started with initially here? And it is. So we've actually learned something right here, so let's go ahead and write that down. I now know that the antiderivative of sine of x is going to be what? Okay, I started out with what I start with, and I took the derivative and I got sine. I start with cosine of x. I'm going to have a constant. But when I take the derivative of cosine, I get negative sine. That means the antiderivative of sine is actually negative cosine of x. So you can either figure that out each time, or you can go ahead and just know that this is the derivative, or the antiderivative, excuse me. Gotta get that straight. Okay, next one, e to the 2x. What did I start with? So when I took the derivative, I got e to the 2x. Well, first thing I know is I started with e to the 2x, because the derivative of e to the 2x is e to the 2x times 2. What about this 2? I don't have this 2 there, which means if I don't have the 2 there, I should have multiplied by a 1/2 or divided by 2. And again, let's go ahead and get a quick check. So if y is 1/2 e to the 2x plus a constant, I take the derivative, my 1/2 stays there, e to the 2x is still e to the 2x, and then I multiply by the derivative of the inside, which is 2. the derivative of a constant is 0. And my 2 and my 1/2 multiply together to give me a 1. So that tells me that it should just be e to the 2x, and this is the same as what I took the antiderivative of. Okay, so that one looks good. Last one, example 4, evaluates the antiderivative of 5 raised to the x. Let's refresh our memory. If I have y is equal to 5 raised to the x, then y prime is going to be 5 raised to the x, and then times that pesky little thing, natural log of my base, which is 5. So that should help me in actually finding my antiderivative. So I know that I should have a 5 to the x in my antiderivative. So again, my antiderivative, I'm going to have a 5 raised to the x. Now, but when I take the derivative of 5 raised to the x, I get 5 raised to the x times natural log of 5. I don't have a natural log of 5 in my initial problem, so that means I need to multiply by 1 over natural log of 5. So again, let's give it a check. So y I'm saying is equal to 1 over natural log of 5 times 5 raised to the x plus some constant. Let's take our derivative. The constant in the front, the 1 over natural log 5, which is just a number, is just going to stay. I multiply by the derivative of 5 raised to the x, which is 5 raised to the x times natural log of 5. The derivative of my constant is 0. Now these guys, here and here, 1 over natural log of 5 times the natural log of 5 is just 1. So that tells me that y prime would be 5 raised to the x, and this is what I started with right here. Okay, so I like that one as well. There you go. That's our introduction to antiderivatives, and we will be practicing quite a few more once we get into class. So I hope you have a wonderful, wonderful evening.